hardware from a specification using AI. Can AI really generate hardware from a specification? It may not matter because that's only a small part of the problem. There is a lot of excitement these days surrounding the idea that it could make it possible to go from a specification to design with absolutely not hardware skills. Well, get in line because there is an umpteenth potential technology that was going to make that possible. Don't get me wrong, it just might do it. But will this in an implementation that is reliable, having decent performance, use the minimum possible energy, be secure from the health, work under extreme conditions, be cost effective, and may have the Earth software and actually turn it from a piece of silicon into a viable product. 30 years ago, I worked on a project that was designed to go from a specification, enable hardware software partitioning onto a predefined platform. Then they enabled the hardware to be synthesized and implemented using an enhanced flow, starting out with a high-level synthesis, as I was not alone. Most of the major EDA companies and many of the leading-edge semiconductor companies were behind this effort, and a lot of money was poured into it. We can see only a couple of remnants of today's high-level synthesis and virtual prototyping, and the two things railroaded the effort. First, it was the same that the notion of the IP were entering into picture. This meant not all of the design would start from a specification that had to be implemented. Instead, a significant portion of the problem because one is selection and integration. This methodology finish up is being barely used successful and significantly reduced design times, even though its impact of the verification was much less. This is why the teams now spend more hours on verification than on design. The second issue was the lack of the models. To build a virtual prototype, you needed to verify the models at the correct level of abstraction and the appropriate performance. Those three words, models, abstraction, and performance, pretty much killed the effort, even though some do survive and are doing quite well within a limited scope application. The key is that abstraction and performance are opposing concepts. To get a performance, you have to give up something in terms of abstraction and vice versa. But the more abstract you become, the greater the potential gains they have to be. Such that the fidelity of the result does not mean that your noise is greater than your signal. The next effort was the extension to the high-level synthesis, which could take a software and create a hardware from it could be implemented in FPGAs. It was thought that it would increase the number of hardware developers by 100-fold, and software engineers would be able to do this without a lot of hardware knowledge. It was thought that it was any hardware, no more matter how inefficient, would be still than a software running on a single-threaded CPU. The problem was that a solution was expensive. It was not that easy to integrate an FPGA with the CPU, which was still required to run the pieces that could be turned into a hardware. And the context switch times between them that often exceeded the speed that was gained. AI does have a few things going for it. The first is that it may be able to quickly and accurately generate models with the correct abstraction for task at hand. These ultimately tells many models, each of the different set of characteristics. One model to be architectural analysis, a different model for performance, timing, power, and etc. analysis. And yet another model can be used for verification. The cost of doing model validation is high, and if it cannot be significantly reduced, and it is non-starter. The next thing is that the systems these days are the software century. If the custom CPUs start with the application, they are meant to run and look at how the CPU can be tailored to the workflow. Unlike a FPGA solution, this is extension of the processor that targets frequently executed code and tightly integrated, meaning there is no context switch. It can thus target much faster, much finer graduality of the acceleration, but every such processor still have to be verified as already mentioned, this takes more than the design, so by Amdahl's law, it has a small gain in terms of development cost than may have been expected. But I heard you say that AI will make it correct by construction, meaning you don't have to do verification. My response, I have never in my whole career seen a specification that is complete, correct, and unambiguous. Tell me you are prepared to go to Silicon without a performance verification, and I will run for the hills far away from your product. This is the biggest problem, and I do not see any indication that it will be solved in near future. Go back into the demise of the ESL. It was about the IP. AI has a good chance to do the IP selection and integration. The IP blocks have been pre-verified, and while you still need to some levels of integration verification, this might be manageable. It is even possible that the small chunk of it could be run through the HLS to put in some customer algorithms or the acceleration. The HSL flows do have some fairly advanced verification built into them, including sequential equivalency checking to ensure that was generated by the tools matched the input specification. But you still have to find out if this specification is correct, and you can use the same tool to do it that was used for design. Verification is about comparing two things that you can find the differences. Whenever I heard someone says it will be possible to generate hardware using AI, I first want to find out about their expectation and the limitations they are willing to consider, and the business model that goes along with the product they want to make. After the discussion, I will be willing to admit that the virtue stands a chance, but I don't think we are there yet for many cases. How long before we get there? No one knows for sure.